Today we're going to talk about rational functions. This content is in both AA courses, so we're going to start with the SL part and then move on to the HL part. And it all starts with this function, the function 1 over x, which is also called the reciprocal function. And you should know that it has that shape just by thinking about it for a little bit. When you think about x values that are positive on this side, the bigger the denominator of a fraction, the smaller the value of the fraction as a whole. But if x is the positive number, no matter how big it gets, then the fraction itself is still positive. So that makes this shape here, where for bigger values of x, we are getting smaller as a function, which is the value of the fraction, but we are not crossing over to the negative side, so we are still positive. This shape is getting closer to the x-axis. It's making a horizontal asymptote. And the same thing happens on the left for negative values of x. If you have big negative numbers here, the fraction is also going to be very small. Like think of 1 divided by negative 100, for example. So it's also getting closer and closer to 0, but this time it's a negative value because we have a 1 that's positive divided by x, which is negative. So you have this horizontal asymptote of y equals 0 on both sides of the function. But we also have to think about what happens for small values of x, like values of x that are close to 0. And that is the opposite. If a denominator of a fraction is getting smaller, that means that the fraction itself is getting bigger. You should think of examples like these ones to convince yourself of that fact. So we can't ever divide by 0 itself, but we can divide by very, very small numbers. And these are getting smaller. What is the effect of that on the fraction? When we divide by a smaller number, we get a bigger result. So we can't get to dividing by 0 itself, which means that 0 is not in the domain of this function, but we can divide by very small numbers, and the result is a big number, which is why this is happening here. As we get closer to 0, the function gets bigger. The same thing happens on the other side, but with negative numbers, because if you divide a positive by a negative, you get a negative. So that's this behavior over here. Either way, what we can see is that now we have a vertical asymptote at x equals 0. And I know that it's common for people to ask, but how can one function have two parts of the graph? This is a very common question. It is a very reasonable question, but the answer is in all of the comments that we've already made today. Because if you're going to follow all of these rules, all of these features of this function that we were just discussing, then this is the only way to put it in the graph altogether. So this is why, this is how come one function can have two parts of the graph, so to speak. And notice that you break from one part to the other part exactly where you have a break in the domain. You have a number that is not in the domain, which is x equals 0. So that creates this opportunity for the function to break into two parts, and some functions actually do that, which is the case of this one. Okay, so that was a good start, but that's not all there is to rational functions. Something that we can easily do now is to start thinking of graphic transformations on this function. For example, we could do a horizontal translation. So we do horizontal translations by adding a number to x. The x-axis works backwards in terms of transformation, so moving x plus 3 has made me shift my whole function to the left. The number that is outside of the domain now is not 0 anymore, because it's perfectly fine to have x equals 0 here. The answer will just be 1 over 3. But we can't have x equals to negative 3 in this function, because then we would have in the denominator negative 3 plus 3, which is 0. We would be attempting to divide by 0, which is not possible. So x negative 3 is not in the domain of the function. It becomes a vertical asymptote, just like points that are outside of the domain very often do. I should remind you also that in a sketch of a function, we are supposed to place the asymptotes there as a dashed line, and that there has been no change vertically here. The horizontal asymptote is still at the same place as it used to be, because the only translation that we did so far was horizontal. But something that has changed as a consequence of that is that my function now has a y-intercept, which the previous one didn't have, because y-intercept is f of 0, and 0 wasn't even in the domain of that function, so it didn't have a y-intercept. But this one does. And f of 0, like we've already said, is 1 over 3. And this function still does not have an x-intercept, just because of the horizontal asymptote. But we can change that by now doing a vertical translation. So let's take this function and shift it up a little bit, so that maybe this point is going to go up and cross the horizontal axis. So let's take a look at all of the consequences of that vertical translation. I have added one here, adding one to the function that I already had instead of adding to the x this time, because vertical transformations are vertical. So you should do the +1 on whatever was the y, not on the x. The domain hasn't changed when I did that, because the only domain restriction that I'm dealing with here is the fact that we can't divide by 0, and I didn't change the thing that I'm dividing by. It's still x plus 3. So the vertical asymptote also hasn't changed. It remains at x equals -3. The x-intercept that I was trying to get is there. I'm still going to calculate what it is. And the horizontal asymptote, which used to be the axis itself, it used to be y equals 0. Now the asymptote has shifted up as well, because when we do a vertical translation, we're taking the whole function, every point of the function, and we're shifting it up by the same amount. So in particular, if we're doing that to these points here, that we're getting close to the asymptote, they have moved up, but they are still getting close to the asymptote. So that means that the asymptote must have gone up as well by the same amount. And also the y-intercept has shifted up by 1, so it used to be 1 over 3, now it's 4 over 3, which is f of 0, a third plus 1. In order to calculate the value of the x-intercept, we need to ask the equation, for what value of x is f of x equal to 0? And then we have to calculate that. So we have this function equal to 0. Let's subtract 1 on both sides. Now we can multiply both sides by x plus 3, distribute the minus. Now maybe I want to add x to both sides and subtract 1. So the result here is going to be -4. Which makes sense over there, right? It's a little bit to the left of the asymptote that is x equals -3, so -4 is a value that makes sense. Okay, so a lot of the time in exercises about rational functions, the expression of the function is not going to be given to you in this way, like a fraction plus a number. We can just add those two parts into one fraction, and that is the kind of thing that you will usually see in a question about rational functions. So in the example, I showed you the horizontal translation and vertical translation. I didn't show you stretches, but the stretch also keeps the shape of the function, right? It's going to be a little wider or maybe a little taller, depending on how much of a stretch you do in each direction, but it's still going to be the same kind of function, something that has two parts, one here, one there, and it has a horizontal asymptote and a vertical asymptote. Maybe the two parts are like this instead, if you do also a reflection transformation. And the way that these things are going to be reflected in what kinds of expressions for the function we can see is that there's also going to be numbers multiplying x here. For example, a horizontal stretch, I have multiplied both x's by 2. But maybe I also want to do on top of that a vertical stretch by multiplying the function itself by 3. So now the two x's are multiplied by different numbers. And if I do a vertical reflection like I was mentioning, then now we have a negative sign there as well. So let's start with a different example and see what we are able to do with it. Usually, this type of function will appear in a very simple question. It's going to be like 5 marks, and it's asking you to make a sketch, okay? So making sketches is something that you know you have to show all relevant features of the function. And for this type of function, we have 4 relevant features. The horizontal asymptote and the vertical asymptote are always there. And sometimes we also have the y-intercept, and sometimes we also have the x-intercept, and that's depending on where the asymptotes are. But the basic idea is that you know you have these 4 features, so you're going to get a mark for finding out each one of them. And you also know the basic shape of the function, so you'll get maybe a 5th mark for connecting the dots correctly in a sketch. So let's do it like this. Vertical asymptote first. Vertical asymptote is a vertical line at a value of x that is outside of the domain. Who is outside of the domain here? X equals 1, because I can't divide by 0. So that is the vertical asymptote. And by the way, a common mistake here is if they ask you to write down the equation of the asymptote, the equation includes the x equals, okay? If you just say 1, 1 is not the equation of the asymptote because 1 is not an equation, 1 is a number. So if they ask you for an equation, you have to tell them the equation. So anyway, next on the list, the y-intercept. How do we find y-intercept? And not only this, but any function. Y-intercept is f of 0. So you're just going to substitute 0 for the x's here, 0, 0. So f of 0 is -7. And what about x-intercept? How do you always do that? You take the function, set it equal to 0, and then solve an equation. In this case, we can start by multiplying both sides by x minus 1 to get rid of this denominator. Now we can subtract 7 and then divide by 3. And then I left the horizontal asymptote for last because out of the things in this list, I think it's the one that you have fewer other things that you also know to connect it to. Like the intercept, you're just doing the same thing as you do for all functions. The vertical asymptote, you're just thinking about domains of functions, which you have thought about before. But what about the horizontal asymptote? This is maybe a little bit different way of thinking. Because what is a horizontal asymptote? It's what happens to the function horizontally. But horizontally, the value of x, the independent variable, is getting very, very large. And it's not enough to think of 100 or 1,000. You have to think about x being all the way to infinity, which is weird because infinity is not a place and infinity is not a number. It's just what is happening to the value of this fraction when x is very, very large. It's not 100, it's not 1,000, it's way larger than that. So what is going to happen is that if x is really that big, then subtracting 1 maybe doesn't do anything to it. 1 is just 1. But think of x as being a billion. Like, what is taking away 1 from a billion going to do? Nothing. And 7 is also nothing when compared to 3 billion. So the idea of thinking about the horizontal asymptote in this particular kind of function is that the numbers that are being added and subtracted, they're basically not doing anything. The x is so big that those numbers that I'm covering with my hand, they don't matter. It's like the function is just 3x divided by x. And what is 3x divided by x? Well, that's 3. So in short, in order to find the horizontal asymptote of a rational function, what do? You take the coefficient of x on the numerator and the denominator, and you divide one by the other, ignoring everything else. But please try not to memorize that in a vacuum like that, because you're going to forget. The syllabus is very big. You will have many, many things to memorize other than just this one. So you are going to forget if you just memorize that. What I want you to memorize is the idea of what a horizontal asymptote is, the fact that you're looking for what happens to the function when x is very, very big. I want you to be able to think about this comparison between numbers, like 7 is very small compared to 3 billion. And then the mechanical part of it, like take this coefficient and divide by that other coefficient, you can recreate that by yourself if you've memorized the correct thing. So to wrap up this exercise, all that we have to do is put all of these 4 features into the sketch and then connect the dots. So we have a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 3. Now I'm going to mark also the y-intercept and the x-intercept. And the idea is now to connect the dots. But technically speaking, I only have 2 dots, but I also know about the shape of the function. I also know that it has a horizontal asymptote, a vertical asymptote, 2 parts that look like this. So it's not just this dot and this dot. You can think of the asymptote as a kind of dot as well. And the other asymptote is the 4th dot. So you're going to connect all of these 4 things here in the appropriate shape. And I see a lot of students just stop here, which is understandable, but it's also wrong because you know that the function is supposed to have 2 sides. There are no dots on the other side, but there are 2 asymptotes, and you know that the other side is there, so you have to put it in the sketch. Try to make it look kind of symmetric to the other side. Like if this is this far away, don't do the other one like too close or something like that. But that is details, okay? The important thing is for you to not forget to put the other side there. Okay, so that was it for the standard level rational functions. As for higher level, what changes is that now you can have more than one linear factor in the denominator and more than one in the numerator as well. A lot of times more than one is just going to be 2 because then they can distribute this and give it to you as quadratic functions, which looks a little bit pretty. But technically you could do it for any number of linear fractions in the denominator and numerator, especially if they come factored out like this example. Okay, so let's work through this example. What changes here? Well, we still have 4 relevant things to think about, which is horizontal, vertical, and then the intercepts. But one thing that clearly changes here is that the domain restriction now is going to exclude 2 values of x, because x can't be 1 and x can't be negative half. So next, y-intercept. This one I can't have more than one of, right? It's just f of 0, so let's calculate that. X-intercept I can have more than one of. So I have this number and this number, which make this function be 0 because this number makes this factor of the numerator a 0 and then multiplies by something else is still 0. And that number makes that factor of the numerator be equal to 0, so the whole thing is 0. Now, it is an interesting question as to whether I can have more than one horizontal asymptote or not. Because technically what a horizontal asymptote is what happens to the function when x is very large. And I keep pointing very large to that side, but there's also that side. So technically you can have functions that have one behavior when x is very large negative number and a different behavior for x very large positive number. It would look something like this. Function started out getting close to one horizontal line, then it did something in the middle, and then ended in the other side getting very close to a different horizontal line. These things exist. There are interesting functions that do that. But the thing is that rational functions don't. Rational functions don't do that. The behavior that they're going to have on the right side and on the left side is the same. It's not always going to be a horizontal asymptote for the high-level version of rational functions, but when it is a horizontal asymptote, then you have the same one on the right and on the left. And it is the case for this example. It's the same idea here. You can think of what's going to happen when x is very large. So the 7 is irrelevant compared to the 3 billion, and the 3 is irrelevant when compared to the 1 billion. So you can just think of the numerator as 3x times x, which is 3x squared, and then you can think of the denominator for the same reasons as just x times 2x, which is 2x squared. So we're basically just dealing with this function, but x squared cancels out with x squared here, and the result of the function is going to be pretty much just 3 over 2. And this is a kind of exercise that I personally find very, very fun. When we get to this point, we have all of these dots, and now we have to make a sketch connecting all the dots. That is, I just find it very pretty. So here are all the features that we've already talked about, and now I'm going to show you how to connect them. But first, I want to point out that not drawing the sketch to scale is sometimes very important to make your picture look understandable. For example, in this case, I have one of my interesting numbers is -21, which is pretty big compared to all of the other numbers that I have in my sketch. So this is 3/2. This is 3/2 and this is -21. This is definitely not drawn to scale. But this is the way that we want it, okay? Because otherwise things are just too far away or too small and you just can't see them very well. So make use of the fact that a sketch does not need to be to scale and use that because it's going to make for a better sketch. But what you can't mess up is the order of the numbers. So whether -3 and -7/3 are this close to each other or farther apart is irrelevant, but -3 is to the left of -7/3. This you have to pay attention to. So let's begin connecting these dots. I'm going to begin at the -21 because I think it's going to be the easiest of all the ones that are here. Okay, so I start at -21. Where do I go? Do I go up or do I go down? And the answer is that you're going to go down, because if you went up from here and then tried to make this vertical asymptote, you would have to cross the horizontal axis. And you don't want to do that here because you already know that the only x-intercepts are those. You don't want to accidentally make one more. So from here, your only option is to go down. You don't need to make it look symmetric between the vertical asymptotes, okay? The only thing that I was trying to do was to not make it look like the y-intercept was also a local maximum. Because it probably isn't. This would be too much coincidence. So I've made sure to put the local maximum somewhere else. And yes, if you want to be extremely precise, you will also find the coordinates of local maximum. Maybe you know tools of how to do that, but this is not typically the kind of thing that this exercise expects you to do, okay? It stops in the intercept and the asymptote. So don't go crazy. Look at the number of marks of the question, and also if he wants a local maximum, he will specifically ask you for it. So now let's go to this side. I also want to connect this dot of the horizontal asymptote, but how do I know? Is it coming from here or from here? Both of these things are horizontal asymptote at y=3/2. So how am I going to choose one of them? Well, if I choose this one and start going down, then I have the same problem. I can't cross the horizontal axis again because the x-intercepts are all the way over there. I could go down and then come back up before I ever cross the axis, making the vertical asymptote here go up as well, which is going to have to be. So this works, but this also works. And I think I'm going to go with the simpler thing, which is this one. And now let's talk about over there. We have two x-intercepts, which are obviously going to have to connect to each other, but they also have two choices. They can connect to each other through up here or down there. And also over there, if you connect them through the positive side, then you go down here again, but you still need to end up at that horizontal asymptote over there. So to go from here to there, you would need to cross the x-axis again, which is not allowed. So that is the wrong picture. That is the right way to connect the two x-intercepts, and then you go for the horizontal asymptote over there. And over here, you just keep going up until you get to the vertical asymptote. Okay, so I know I said that I wasn't going to do this because this is not part of the typical rational functions exercise, but I couldn't resist it. I did it anyway. So here is the derivative of the function. If we wanted to figure out the turning points, the local maximum and the local minimum, we would take this derivative and set it equal to 0, solve this equation. I'm not going to do that, but I do want to point out that it looks like the numerator would be a polynomial of degree 3 because I have x and x squared here, x squared and x there. It turns out, though, that 6 times 2 is 12, and 3 times 4 is also 12, so the term in x to the power of 3 is going to cancel out. The numerator here is actually a polynomial of degree 2. So this equation equal to 0 is only going to have 2 solutions, and we already have 2 turning points here. So that is a more satisfying explanation as to why this side looks like this and not like the other possible solution that I mentioned before. So the moral of the story here is that there are many interesting ways in which you can figure out how to connect the dots. And it's also not just a straightforward matter of connecting this. You actually do have to think through a bunch of things in the way, in one of many possible interesting ways. I want to mention one more way, though, that I didn't mention when I was making this sketch, because I wanted to show you that there are other possible ways to think about things. But one fact that is going to be sometimes useful for you to know is that every time that you have a vertical asymptote that came from one of these factors in the denominator here, and each factor was just appearing once. What I mean by that is that it could have been appearing twice, right? It could have been x minus 1 squared in the denominator, but it wasn't. So every time that the factor in the denominator that gave rise to the vertical asymptote is just appearing once, you know for sure that if one of the sides goes down, the other side goes up. We could have used that fact when we were doing the sketch here because we started in the negative 21. It was the easiest part. We put them both going down here, and each one of them is just appearing once. So immediately when I did that, I knew that both this one and this one would be coming from above on the other side. If there was the power of 2 here, then it would be the other conclusion, okay? When it is appearing twice, you know that either both sides go up or both sides go down. So what if the factor was appearing 3 times? What do you think? Well, it's about parity, right? An odd number of times you have this behavior of one down and one up, and an even number of times that the factor appears, you will have both going to the same side. Okay, so what else is there in this topic? What could still happen that would be different from the example that we just did, creating other types of interesting situations? And the thing is that I mentioned about the horizontal asymptote, that for this type of function, for rational functions, whatever the behavior is on the right side is going to be the same on the left side. And we saw an example of what happens when there is this horizontal asymptote, which in this case is y equals 3 over 2. But that's not the only kind of behavior that could be happening on both sides. So there are a couple of different scenarios. So the general case for this type of function is that we have f of x, which is a fraction, g of x over h of x, two functions that have to be polynomials. So the different cases that can appear are going to refer to how the degree of those two polynomials relate to each other. The first case that I want to look at is what happens when the degree of the numerator is less than the degree of the denominator, like this one. And still we have to think about what's going to happen when x is a very large number. And in such cases, what's going to happen is that because the degree in the denominator is bigger than the degree in the numerator, so the denominator is growing larger as x gets larger a lot faster. So both numbers are getting big, but this one's getting bigger, so the fraction is going to 0. In this type of situation, you always get the horizontal asymptote on both sides, and that horizontal asymptote is y equals 0. And the second case that we need to look at is the case that was the example that we were examining, where the degree of both the numerator and denominator are the same, in the example that we were looking at, which is the most common one. It was degree 2 over degree 2. So that is the situation in which you can get a horizontal asymptote that is not y equals 0. Like in our example, we had y equals 3 over 2. In general, the asymptote is going to be found by taking the leading coefficient of the g divided by the leading coefficient of the h, and that is for the reasons that we've already discussed. So now after looking at this, you might think that there is just one final case missing, case 3, where the degree of g is bigger than the degree of h, right? It's either smaller, equal, or bigger. But that's not all. I actually want to split that final missing case in 2 parts. First, we're going to analyze what happens when the degree of the numerator is exactly 1 more than the degree of the denominator. So that's going to be things like a quadratic divided by a linear, or a cubic divided by a quadratic. That turns out to be more interesting than if the degree of g is even bigger than that. This final case is not that interesting. The conclusion here that I'm going to write down is that you just don't have an asymptote. And of course, by that I mean that there is no asymptote that happens when x is large. I am not talking about the vertical asymptotes, which of course can still exist. But in this kind of case, we do have an asymptote when x is getting large. It's just not horizontal. This is the case of diagonal asymptotes, which sometimes people also call oblique asymptotes. And I am going to work through the examples, but first I want to try to make you understand why this is the case where this happens, because this is the most interesting of the cases. See, let's start with the simpler one. The case where both of the degrees are the same. So this is the case that has a horizontal asymptote. In fact, degree 1 divided by degree 1 is the standard level type of rational functions that we were talking about in the beginning of the video. So for this one, both leading coefficients are equal to 1. 1 over 1 is 1, so that's the horizontal asymptote that you get on both sides. We also have the vertical asymptote at x equals -1 because of this denominator. F of 0 is 3, and the x-intercept is -3 because that makes the numerator equal to 0. Now we connect the dots to make this function, and now I want you to think about adding this function to a linear function. Like I'm going to do plus 2x as an example. 2x is the green function here, and it's important that we are adding to something of degree 1. That's going to be about this one here, like the difference between the degree of both polynomials. So now I want to think about what the fraction plus 2x function looks like. I want to draw it in red, and I am going to think about this in terms of adding 2 functions graphically. I already have a whole other video about this. That video is not exactly just about this, but I do cover it, so check it out if you want. The idea is that, well, first of all, the addition function is also going to have the same vertical asymptote, because if x equals -1 is not in the domain of the fraction, then it's also not in the domain of the big function that I want to sketch. But over here on this side, notice that the blue function is getting very close to its asymptote of y equals 1. So the values of the blue function are pretty much just 1. And I'm going to add that 1 on top of the 2x function that I have here in green. So that's going to become like 2x plus 1, which is also a straight line. And the same thing is going to happen on the left side as well, because even though these values here are reaching the horizontal asymptote from below instead of reaching it from above like here, they are still values that are pretty close to 1. And so I want to take these values that are very close to 1, a little bit smaller than 1, but very close. I want to take them and I want to add them to the green function 2x. So it's still going to look like 2x plus 1 for sketching effects, because the difference between that and 1 is just very small. It's not visible. So it looks like that. Let's go through a couple of other points. At x equals 0, green is 0, so the red function is also going to go through the same y-intercept. And then as we approach the vertical asymptote, it's going to get very large because after all, it is whatever the blue is, which is very large, plus a very small thing, which is actually a negative number. So the red one is going to be below the blue one. And something similar is going to happen on the other side. Blue is very big and negative. I am adding it to green, which is not so big, but it's also negative. So the red is going to be a little bit below the blue, and this needs to connect to that. So at some point, it's going to have a turning point. But check out the dashed line, 2x plus 1. That is the diagonal asymptote. So the red function is approaching that diagonal line as x goes to infinity because the red function is the blue function plus the green function. And the green function was 2x, the blue was approaching 1. So when you add those two things, it's 2x plus 1, which is this red diagonal line, which then becomes the diagonal asymptote of this rational function. This only happens when you take something that has a horizontal asymptote and therefore the same degree in both sides of the fraction, and you add that to something that has degree 1, which is a line. If you add it to something bigger, like you add it to x squared here, then you also get interesting asymptotic behavior. You're going to get something that looks like a quadratic function as x going to infinity. But that, even though you can call it asymptotic behavior, like it would be a function that has the same asymptotic behavior as a quadratic function, that is not the same as using the word asymptote, because the definition of the word asymptote includes the fact that it is a line. It needs to be a straight line. So that's what this number 1 here is about. It has to be exactly plus 1 because we are adding 1 degree here. But again, in exercises, it doesn't often come split up into 2 parts like this. They usually add the 2 things into just 1 fraction, so let's put it in the same denominator. And that's how the degree of the numerator becomes 1 more than the degree of the denominator, because they used to be the same, and then you multiplied it by this linear fraction, so that's plus 1 in the degree. Okay, so let's go through this example here. I've already added to the sketch all of the easier parts, which are, you can see that f of 0 is -3. You can also see that you have a vertical asymptote at x equals -1, and that the function has 2 zeros, which are plus or minus the square root of 3. So the only thing that we have left to do before connecting the dots is figuring out what the diagonal asymptote is. We need to figure out what the line is, but we already know that there is a diagonal asymptote. That is because we have degree 2 divided by degree 1. So how do we figure out which line? And we are going to work that out by polynomial division. Now, I know that a lot of people hate polynomial division. I'm not one of those people. But I'm sorry, it just has to be that, because a fraction is a division, and the things that we are dividing are polynomials. So what else are we going to do? We're going to do polynomial division. I'm going to do it over here because I don't think I have enough space there. So here is the thing. You have to always follow the same process as if you were just dividing numbers, but always focus just on the first term of both things that you have, okay? So it's not this whole thing going into this whole thing, but just the x going into the x squared. So the result is going to be x, because x squared divided by x is x. And then you take the x multiplied by the whole x plus 1. Now you take the whole thing and you subtract it here. Now you do the same thing again, but just the first term with just the first term, okay? So negative x divided by x is -1, which you're going to put up here. And now you're going to take the -1 and multiply by the whole thing. So it's -x minus 1, and then you're going to subtract those things. That's a lot of minuses, but I believe the answer is -2 here. That's the remainder of the division. And the most important part of the whole thing is this blue stuff that I just wrote here. It's how you interpret the result of this division. So when you divide this polynomial by this polynomial, the answer is x minus 1. So that is equal to x minus 1. But it's not exactly equal to x minus 1 because the remainder was not 0. So you still have that negative 2 there, which was not quite able to divide by x plus 1. That's why it's a remainder, because it wasn't divided. So it still wants to be divided. That's why it is still over x plus 1. And we are doing this whole thing because we are interested in the diagonal asymptote. We are figuring out that this function is equal to this line plus something else that is going to 0, right? That is the kind of function that would have y equals 0 as a horizontal asymptote, because the degree of the numerator is smaller than the degree of the denominator. So in all of this, what is the equation of the diagonal asymptote? It's that one. It's the line that the function wants to be equal to, the quotient of the polynomial division. The function doesn't get to be exactly equal to that line, but it's almost equal. It's just that little bit left. So that's exactly what asymptote means. It's almost equal to that. So we're going to add this x minus 1 line to our sketch. And now we are going to connect all the dots. I'm going to start from here. I know that to the left I need to approach my diagonal asymptote. So to the right of this x-intercept, I'm just going to go up to the vertical asymptote. Again, there was no way to turn around and approach it going down, because then I would need another x-intercept here, and I can't have that. Now I already know that after going up on this vertical asymptote, the other side of the asymptote needs to start from the other side. Why is that? Because the denominator has this factor of x plus 1 only appearing once. That's what we were discussing before. So from there I can go to this dot and to that other dot, and now I need to approach the line again. The function probably doesn't actually have all of these changes in concavity here, right? The function is just a reciprocal function being added to a straight line, so it doesn't do that. This is happening just because of imprecision in the sketch, the fact that things aren't to scale. This is the square root of 3 and this is 3. You can fix that if you want by erasing the points, putting the curve first, and then marking the points where they need to be. There, this looks a lot more appropriate. So let's mark the square root of 3 here and the negative 3 here. So here is the other example that I said I was also going to do. This one has 3 zeros at x equals 1, 2, and 3, and it has 2 vertical asymptotes at x equals plus or minus the square root of 7. Here's the kind of thing that you have to pay attention to, because the square root of 7 is a number between 2 and 3, so the asymptote needs to be here. The y-intercept f of 0 is negative 6 divided by negative 7, so it's a positive number. And in order to figure out the equation of the diagonal asymptote, we needed to distribute all of the factors in the numerator, because now I want to do the numerator divided by the denominator. And again, I already know that there is going to be a diagonal asymptote because of the difference in the degrees of these things. This one is degree 3, this one is degree 2. So when I divide one by the other, the quotient is going to be something in degree 1, which is the diagonal asymptote that we are looking for. X cubed divided by x squared is x. Now x times this thing is x cubed minus 7x, which needs to be subtracted from this. And now we do it again. Minus 6x squared divided by x squared is just minus 6. This times this is this, needs to be subtracted from this. But actually, we don't need to execute this part of the polynomial division, because our answer is already here. X minus 6 is the quotient of the division, so it is the equation of the diagonal asymptote. We don't need the remainder for anything. We just need to be careful to place the x minus 6 line here correctly with respect to the other things that are already in the graph. For example, The farthest to the right point that I have here is 3. So when x equals 3, 3 minus 6 is negative 3. So the line needs to go down here, under everything else. And you can see that this is a little bit difficult to draw sometimes. I ran out of space in the corner there, so there's a part of the sketch that I can't see very well. I'm going to erase this and do it again, keeping this in mind, that I'm going to need more space in the bottom than I'm needing on the top, so I'm going to shift everything up. That's better. So now let's begin connecting the dots. This 3 needs to connect to the diagonal asymptote. It can go like this, and the other option was for it to go down here, but that's not possible because we'd need to cross the x's again. So it is the top one. And then on the other side of the negative 3, it needs to go to the vertical asymptote going down for the exact same reason. It couldn't go up because then it would need to turn around and cross the x-axis. But I want to point something out here because a lot of people get nervous with things like what's happening in this point. The function is crossing the dashed line that is the diagonal asymptote. And a lot of people get nervous with things like that because they are convinced that the function shouldn't cross its own asymptote. However, I do want to point out that this is very much not the case. Things like this happen all the time. A function can't cross through a vertical asymptote. That's true, because the vertical asymptote is a point that is outside of the domain. So if it's not in the domain, the function can't go through there. But that's just vertical asymptotes. As for the other asymptotes, horizontal or diagonal, the definition of asymptote is that the function gets close to that line when x is very large. You can cross as much as you want, as long as for x very large you are not getting far away from it. That's the only thing that would contradict the definition. So crossing does not contradict the definition of asymptote. It's still getting closer to it when x is very large. So the fact that it crossed here didn't have any effect on that. So let's move on. This denominator has a square, but that is not the same factor twice. It's x minus the square root of 7 times x plus the square root of 7. That's why we have two vertical asymptotes, and each one of these factors is only appearing once. So if the function went down here, it needs to come from above over here. It's going to go through this point, that point, and then it's going to go up in the vertical asymptote. I don't quite have enough space to draw that here, but I'm going to make space. There you go. And that vertical asymptote also comes from a factor in the denominator that was only appearing once. So if I went up there, I have to go down here, and then I'm going to connect to the diagonal asymptote on the left. And that's the final sketch for this exercise. But wait a second, this has been bothering me because I didn't pick those numbers specifically so that 6 times 2 was going to be equal to 3 times 4. That was a coincidence, and it feels like too much of a coincidence. So now I'm wondering if that always happens. If every time that I have a quadratic divided by another quadratic, if that function is only allowed to have 2 turning points all the time. So in order to check if this is true, I can't deal with examples anymore, so that's why I have all those letters there, A, B, C, K, M, N. Obviously, we are assuming A and K are not 0 because otherwise that would change the degree of those polynomials. And what I'm going to do here is just take the derivative and set it equal to 0 and see what happens. But before I do that, I also wanted to point out that usually I don't like teaching this subject in generality like this with A, B, C. I always like to teach only through examples because I feel that what happens if I try to do things in generality with all letters, in the end we get a formula. That's inevitable. Instead of getting numbers like we were getting for our examples, those numbers are going to be formulas depending on A, B, C, K, M, N. And I don't like that that happens in class, because if it does, then you get a formula and the students try to memorize it. So that is counterproductive, and I don't like doing that. But for something like this, it's inevitable because I want to check if something always happens, and examples are not going to tell me anything about always. So let's go take the derivative of this. We're going to use the quotient rule. I had to get out of the way here so that you can see the whole thing because it's a big expression. But that is the derivative of the function, and in order to find the turning points, we want to set that equal to 0. We don't need the denominator for that because it's just going to be the numerator equal to 0. And the question is about how many solutions this can have. Well, that depends on the degree of the polynomial, because a polynomial of degree k can have at most k solutions. Here, it looks like the polynomial should have degree 3, but the only terms in degree 3 are these two that I marked in green and orange, and you can see that they are both the same. They are 2akx cubed, and then we're going to subtract one from the other. Yes, they are always going to cancel out. So this is a very pretty fact that I never knew before. And the last thing that I wanted to very quickly point out, I'm not going to do this exercise all the way to the end because this kind of thing I don't think fits in very well with the content of the syllabus, unless they were really guiding you through it, like a paper 3 question, part A, do this, part B, do that. But that's not what I want to say. I just wanted to point out that diagonal asymptotes are a beautiful thing that we study in this context of rational functions. But they are not exclusive to rational functions. This is not a rational function, but a lot of other things can have diagonal asymptotes as well. But the polynomial division doesn't help us find which one it is because this is not a polynomial division to do. So in general, how can you figure out if a function has a diagonal asymptote, and if it does, what is the equation of the diagonal asymptote? So there are basically two different methods that people use for this kind of thing. First of all, if there is a diagonal asymptote ax plus b, then the difference between the function and the asymptote is going to go to 0 in the limit as x goes to infinity. This is the definition of asymptote. So you could try to work with calculating a limit like this one. In this case, I'm putting a equals 1 and b equals 0 because I have reason to believe that that is the diagonal asymptote. But calculating this kind of limit is annoying because x is going to infinity, so this is going to infinity, and this is going to infinity as well. But infinity minus infinity, you can't just go ahead and claim that it's 0 because this is one of the indeterminate forms. So you need another kind of trick to actually calculate this limit. I don't hate this trick. You could call it reverse rationalization. If this is the first time you're ever seeing something like this, then it's going to feel like a brilliant idea that came out of absolutely nowhere, but it's not. This kind of trick happens over and over in different situations, and it's useful because now I have an x squared minus x squared up here, and now I have a limit that is very clearly just 3 divided by something that goes to infinity. That is 0. So that is a valid method for finding diagonal asymptotes, but it's not my favorite. I prefer method number 2. If a function has a diagonal asymptote, then as x goes to infinity, it approaches a line, and a line is something with constant slope a, if the line is y equals ax plus b. So the derivative of the function is getting close to just a constant number. The idea for method 2 then is to take your function, look at its derivative, just find the limit of that derivative as x is going to infinity and see if that is a number. So here is the derivative of a function, and you can kind of see that this limit wants to be 1, right? Because as x goes to infinity, the 3 doesn't matter, and the square root of x squared is just x, cancels with the x above. That is not a very precise way to deal with limits. So the standard trick that we do in a situation like this is to factor out the x squared from this square root denominator. That's better because now you can say that as x goes to infinity, this fraction with x squared in the denominator is going to 0, so this square root is just 1, and this crosses out with that. And there's also a third thing that you can do, which is more similar to method 1 than method 2 in the sense that it doesn't involve derivatives, but it's more similar to method 2 than 1 in the sense that you don't need an initial idea of what the slope of the diagonal asymptote is going to be. You just say, well, if there is a diagonal asymptote y equals ax plus b, again, as x goes to infinity, the function is approaching that ax plus b. X is big, so b doesn't matter when compared to ax. So you just take the function divided by x, and the result of that should be a, because the function is going to ax. Ax over x should be a. That limit is an indeterminate form as well. It is infinity over infinity, but we're going to solve that with pretty much the same trick as the last one we just did. We factored out the x squared here, so this fraction is going to 0, this square root is going to 1, this cancels with this, and the answer is 1, which is the slope of the diagonal asymptote of that function. But any way that you choose to find the value of a, you still need to find the value of b. So you go back to method 1, right? It's the function minus ax, the difference between those two things as x is going all the way to the right. That difference is the b of the line y equals ax plus b. And then you calculate another limit to find that. I'm not going to do it because I already did this one in method 1.